Review for exam 4, chapter 14 and 15 on acids and bases. Right. I've got a few highlighted here. Let's see, chapter 14, we're going to start with number 1. Which of the following is a conjugate acid-base pair? Remember what's required for an acid-base pair. If you have an acid reacting with water, say, and protons transferred to water, this is what you have left over. Okay, that's all aqueous solution. I didn't write that in. This is your acid. This is your conjugate base. And while we're here, water becomes a base, and this is its conjugate acid. Two things you'll notice about acid-base pairs. Let's see. Yeah. One is only one proton transferred at a time. I bet that's Jada. Yep. Okay. One proton at a time. So we lost one proton here. We ended up with its conjugate base. The other thing you'll notice is this part of the molecule is the same on both sides. If that's not the case, then you can't have an acid-base pair. And if you transfer more than one proton, you can't have an acid-base pair. So that's what we're looking for with these selections. A through D, and more than one of these, possibly. All right, for the first one, we do have one proton missing in the base side. When we go like this, and OCl minus, the proton's missing, but we've changed this part of the molecule, right? From the chloride to the hypochlorite. So this one is not an acid-base pair. The next one, I think that's the way it goes. Yep. We've transferred two protons, right? This is still the same, but you can't transfer two protons and have an acid-base pair. Ammonia, ammonium, and ammonia. Okay. We could also write this one as NH3 and then another hydrogen out here. So that illustrates the point that this part of the molecule is still the same, and we've only lost one proton. That is an acid-base pair. And the last one, what you've got here is you've gone from 3 protons to 1. That's 2 protons missing. We can't do that for an acid-base pair. All right, so this one can't be true either. C is the answer for those reasons. All right, number 2. The hydrogen sulfate or bisulfate ion can act as either an acid or a base in water solution. In which of the following equations does HSO4 minus act as an acid? Okay, if this is going to be an acid in aqueous solution, it has to be the donor. It has to donate a proton. So what's left over? 2 minus. Okay. Notice that when we lost that proton, we gained another charge. because the bond that broke here took that proton and put it over here as a positive charge, just the proton, not the electrons. Electrons are left behind. So we increase the charge on this ion by one minus. So which one is that? It looks like D. D satisfies those conditions. And we got 3. Which of the following is the equilibrium constant expression for the dissociation of the weak acid HOCl? Actually, it's the ionization, but we sort of use those words interchangeably, dissociation. Technically, dissociation is applied to bases because they're ionic. All you have to do is dissociate the ions. But acids are covalent, so you have to ionize them. HOCl, okay, this is if you notice from the selections, we don't have hydroniums in there. We have hydrogen ions. So this is the reduced shorthand version. So we would write it like this, right? And this is an aqueous solution. These are all in aqueous solution, which means those terms must be included in the expression. So the acid ionization constant for this one would have to be hydrogen ions, hypochlorite ions, and the undissociated hypochlorous acid, like that. And that would be A is your best selection there. All right, let's take a look at number 6. A solution in which the pOH is 12.1 would be described as what? I prefer to assess a solution's acidity or basicity based upon the pH. That's more intuitive to me. So what I would do is take this expression where pH plus pOH equals 14. That means pH is 14 minus 12.1, which would be 1.9 pH. That's definitely strongly acidic, very acidic. That's why A is the best answer for that one. Now, if another method works for you, that's fine. This is the way I think of it. Number 7. Which of the following indicates the most basic solution? Okay. All right, what do we have? We have hydrogen ions concentration as 1 times 10 to the minus 10. 10 to the minus 10 molar. Then we have pOH at 6.7. Then we have hydroxide at 7 times 10 to the minus 5. Then we have pH 4.2. And then at least 2 of the solutions are equal. All right. So right now we've got apples and oranges. Right? In order to make that determination of which is the most basic, we need a common unit of measure. And I would go for pH. So this is easy. pH here is 10. Right? Negative log of 10 to the minus 10 is 10. pOH is 6.7, right? If we take that one and subtract it from 14, we get 0.3, and 6 from 13 is 7, 7.3. Okay. This one takes a little more work. I need my calculator. I need to calculate pOH and then pH from that. So pOH equals the negative log of that value, 7 exponent 5 there. Take the log and change the sign. That's 4.2. So the pH then would be 14 minus that, which would be 18. No, I did it wrong. 4.2 enter 14. 9.8. That's the pH. And here the pH is given. So now we can compare because they were all the same unit of measure, right? The most basic has the highest pH, which is this one. Okay? Right, that was 7, 8. Which of the following solutions contains the strongest acid? I'm not going to write all of them up here. We'll work from the document instead. And I threw this extra question in there, which is the strongest conjugate base? We're going to do the strongest acid first. So if we look at each one of those, when we talk about the strength of an acid, the concentration doesn't matter. What matters is the equilibrium constant, right? The acid dissociation constant is where we get the chemical definition for strength. And you'll notice that we've got for A is 10 to the minus 10. I will put that up there. 10 to the minus 10. B is 10 to the minus 5. It also has a 10 to the minus 12. That's because it's diprotic. It has 2 protons. This is 1 for each of them. And then C has 10 to the minus 5. And D has 10 to the minus 8. And E is 10 to the minus 4. Okay? The reason I only wrote the powers of 10 is because if you compare the orders of magnitude, sometimes you can get the answer very quickly. The only time you need to look at the coefficients for the Ka values is if you have a tie with the exponents, right? And we're looking for the strongest acid. If this was the highest, the largest K value, which gives you the strongest acid, then we would have to go to the coefficients to break the tie. But this one is the strongest one. Right? This is a larger K value than any of the others based upon the powers of 10. This one was put in there to throw you off. What you'll notice is that the first K, or the first proton, is always the largest. So if you're looking for the K that controls the pH for that solution, you look at the first one. That controls the pH. But this one is the strongest acid. Okay? Which one has the strongest conjugate base? The strongest conjugate base comes from the weakest acid. And the weakest acid is this one. Right? This will produce the strongest conjugate base. Okay. I think that's why I threw that one in there, just to make that point. Number 9. Which of the following statements are true? All right. D and E. The pH of a strong acid is always lower than the pH of a weak acid. Think about this. We just covered what determines a strong acid. What determines the pH? The strength of an acid is an intensive property. Right? It doesn't matter what the concentration is. But the pH is dependent upon concentration. That's an extensive property. And the pH of a strong acid doesn't necessarily have to be lower than the pH of a weak acid. If the weak acid has a higher concentration, significantly higher than a strong acid, then it may very well have a lower pH than the strong acid. So A is false. The pH B. The pH of a solution can never be negative. All right? All we have to do is find one example where the pH is negative, and that nullifies B. So what about, say you have hydrochloric acid, and it's and molar. Okay, negative log of 10 is what? Well, it's the power of 10 that equals that value, as long as we make it negative. So if we do this calculation, then this is -1. pH solution can never be negative. That's a false statement. About C, for a conjugate acid-base pair, Ka equals 1 over Kb. Is that true? You just need to know the definition. Right? If you've got, remember, Kw equals Ka times Kb. That means that Ka equals Kw divided by Kb. That statement is false, as given. All right. At least 2 of the statements are true. All the statements are false. False. That one's true. Number 11. For the stepwise dissociation of aqueous H3PO4, which of the following is not a conjugate acid-base pair? All right. So why do we say stepwise dissociation? It should be stepwise ionization. Because, and we're going to use the abbreviated form here. The first ionization gives you this. The second ionization gives you this. And the third ionization gives you this. Okay? So if we're looking for conjugate acid-base pair, we want these two, or these two, or these two. It would be conjugate acid-base pair. And it looks like which of the following is not a conjugate acid-base pair? So the first one says HPO4 and PO3 minus, right? A is correct. That one's good. B, H3PO4 and H2PO4 minus. That one's also good. C, H2PO4 minus and HPO4 2 minus. That one's good. D says H2PO4 and PO4 3 minus. That one's not good. Okay. And we threw one in there, which is still valid because we're in an aqueous solution. So is H3O plus and H2O, is that an acid-base pair? Oh, yeah. Yeah. The hydronium ion loses a proton and produces water. That's the conjugate base. So E is also true. The only one that's false is D. All right. Take a look at 12. For which of the following 0.1 molar diprotic acids with the second dissociation affect the pH significantly? Most often, the second dissociation constant is probably 4 or 5 orders of magnitude smaller than the first. And we look at each one, A, B, C, D, and E. And this one is how many orders of magnitude different? It's about 5. 5 powers of 10. So that one, the second one, will not impact the pH of the solution. Let's see, B is about 4 orders of magnitude. C is 4 and minus 9 is roughly 5 orders of magnitude difference. Okay, probably should do it this way. There. And D says minus 3, 1.8 times 10 to the minus 3 versus the second ionization, 9.3 times 10 to the minus 4. Right? This is almost 2. This is almost 1. If we make this one 1, that's 10 to the minus 3. So this would be approximately 1 times 10 to the minus 3. This would be approximately 2 times 10 to the minus 3. This one is only twice as large as that one. This one would significantly impact the pH of the solution because it's so close to this one. So this is the one where the second ionization constant would cause the pH to be significantly impacted by the second dissociation. And then E is false. We just proved that D is correct, so E can't be true. Right. We'll skip a couple. Get down to 16. Which of the following would give the highest pH when dissolved in water to form a 0.1 molar solution? The highest pH. We're looking for highest pH out of these possibilities. Let's see, a strong acid. Strong acid. Weak acid? Yep. Weak acid. Potassium salt of a weak acid. So potassium salt of a weak acid. And a potassium salt of a strong acid. Strong acid. And E, ammonium salt of a strong acid. Ammonium salt of a strong acid. Okay. Which would give the highest pH? We can throw the strong acid and the weak acid out because we have salts to deal with. And salts, well, salts can either be basic or acidic. But since we've got potassium salts, where did the potassium come from theoretically? It came from a strong base. A strong base and a weak acid yields a basic solution. Okay, that's this one. Okay, and it's going to be a strongly basic solution. Why? Because a weak acid, when it dissociates, produces this strong base. Right? So C is going to produce a strong base. Strong acid, weak acid, they're going to produce acidic solutions. We don't even have to consider those. Potassium salt and a strong acid yields a neutral solution. So that one doesn't work. The only other possibility we have here is ammonium salt and a strong acid. Ammonium comes from a weak base, so it's relatively strong acid. But the strong acid, which would produce acid and a strong acid, this would be probably acidic. This probably would be, not greater than, less than 7. So this is our best choice. C. C should give you the highest pH out of that group. Let's see. Select the answers that best describe an aqueous solution made from each of the following substances. Okay, so 19 and 20. Okay. We want to describe acid, basic, neutral, can't tell. Okay, for each one of these. So we're going to go to 19 first. All right, 19. We've got a ammonium acetate. Ammonium acetate, okay, in aqueous solution produces ammonium plus acetate. Okay. The acid, right, the Ka for this one is 5.6 times 10 to the minus 10. This is the Ka. This would have a Kb because if we put that in solution, it's going to react with water and it's going to take a proton and produce a basic solution. So we need the Kb for this one. And we're comparing the Ka of this cation with the Kb of this, Ka of this cation and the Kb of this anion. And this one is also 5.6 times 10 to the minus 10. So there's a competition going on here. The one that has the largest value tells you whether the solution is going to be acidic or basic. If this one has a larger value, the solution will be acidic. If this one has a larger value, the solution will be basic. And that's if and only if you have a one-to-one relationship here. If you have a situation where you've got multiples of one or the other, then that affects the stoichiometry. And since pH is based upon concentration, the 0.1 molar solution would have a different concentration for the cations and anions. And then you have to consider that also. But since these are one-to-one, then these two are equal. that means this solution is neutral. All right. Let's see. Number 20. Let's see. I'll just go ahead and write it down here. So on this one, we have ammonium perchlorate. Ammonium perchlorate, ClO4. Okay. And we're going to put that in solution. And it's going to produce ammonium with the same Ka as before. And then the perchlorate ion and let's see, it has a Kb of 10 to the minus 21. 10 to the minus 21, approximately. This is the Kb. And the Ka for this one is already given. Okay, so since this one wins, and it's a Ka, this solution is going to be acidic. Now that's the judgment of Ka compared to Kb for the cation and the anion. But the rule of thumb tells us that this is from a weak base versus a strong acid. What strong acid would that be? Perchloric acid. Extremely strong. So strong acid, weak base means the solution's acidic. That's the qualitative assessment. The quantitative assessment says the same thing based upon the comparison of the Kas and the Kbs. So this will be an acidic solution. Now, number 22. Which factor listed below is most important in determining the strength of an oxyacid? Okay. What's an oxyacid? Well, we could say something like this. HO, something out here. It's got at least one oxygen, and this can be a number of different oxygens, right? It could have more than one. So what's the factor that's most important in determining the strength of an oxyacid? We don't even have to look at the selections. We know that as you increase the number, right, as N increases, strength increases. So which one satisfies that? The number of oxygen atoms present in the molecule, D, that determines the strength of this acid. That's the most important factor for oxyacids. 24. Which of the species below, when dissolved in water, will not produce a basic solution? All right. So we have A, B, C, D, and E. And A is SO2, NH3, BaO, 2, and none. So the question is, which, when dissolved in water, will not produce a basic solution? All right. This one's obvious. Right? You dissolve that in water, you get an Arrhenius base. The hydroxide dissociates, makes a basic solution. This is basic. We've looked at ammonia before. Ammonia plus water yields ammonium hydroxide. or the hydroxide ion. This is definitely basic. What happens when you dissolve barium oxide in water? Barium oxide in water produces barium hydroxide. Okay, so that's basic. And this is a metal oxide. Metal oxides always produce basic solutions. This is a non-metal oxide. What does this produce? When it reacts with water, it produces H2SO3. This is acidic. So A is the one that does not produce a basic solution. That's the evidence, but the rule says non-metal oxides dissolved in water produce acidic solutions. Metal oxides dissolved in water produce basic solutions. All right. Lewis acids and bases. All right. Well, let's review acids and bases. We're going to skip Arrhenius definition. We're going to go to Bronsted-Lowry. Before we do the question, Bronsted-Lowry says what? Bronsted-Lowry says an acid is a proton donor, and a base is a proton acceptor. Okay? So Lewis can easily follow from that definition. Proton donor does what? It accepts an electron pair. Electron pair acceptor. That's a Lewis acid. And an electron pair donor is a Lewis base. Okay, so that's what we're looking for. Which of the species here, so 25, we're looking at these selections. Which of the following species cannot act as a Lewis base? A Lewis base is an electron pair donor. So what do we have with O2 minus? We have lots of electrons, right? We have lots of electrons. If we drew the Lewis structure, we would have, well, we'd start off with that, and then two more minuses. There you go. You got lots of electron pairs there, right? So that can act as a Lewis base. OH minus would look like this. Okay? That's also a good electron pair donor. How about this one? CH4. If we drew the Lewis structure, that doesn't have any electron pairs to donate, right? They're all bound up in covalent bonds. This is not a good Lewis base. And if we look at H2S, it would look like water. Right? That's a good electron pair donor. And ammonia, by the same token, right, has an electron pair. So this one is the one that does not act as a Lewis base. Which one can't act as a Lewis base for 26? Okay, we have N3 minus NH2 minus, NH2 minus, NH3, and NH4 plus. Okay. If we start from here, how many lone pairs do we have? Lone pair electrons. This one, we just drew it. It has one lone pair. Take away hydrogen, you got an extra lone pair. Take away another one, you got an extra lone pair. Take away the hydrogen, you got 4 lone pairs. These can all act as Lewis bases. In fact, this is an extremely strong Lewis base, the strongest of this group. This one is like, it's like methane. It has no lone pairs. This one cannot act as a Lewis base. Now it can act as a Lewis acid, right? Electron pair acceptor, yeah, it can do that, but not as a base. All right, number 27. Which of the following cannot act as a Lewis acid? Okay, we want something that cannot accept a pair of electrons. If you've got a cation of any kind, it will accept an electron pair. Right? This one, this one, this one, this one. That one has no more room for electron pairs. Right? It's already got a pair of electrons. It doesn't want any more. No more. So E would not act as a Lewis acid. It would definitely act as a Lewis base. No problem there, but not as a Lewis acid. All right, number 30. Let's see, do I need to leave that other stuff up here? Yeah, the weakest base. No, I don't think so. We're still in chapter 14. Given the following values of pKa, determine which is the weakest base of the answers listed. All right. We got 30. And we have, out of this selection, we have ClO2 minus, right? We have ClO minus. We have HCOO minus, and F minus, and Cl minus. Okay, which is the weakest base of these answers listed? So if it's the weakest base, its conjugate acid would be the strongest acid. It would have the lowest pKa. Right? So if we go to the conjugate acid side, right, we need to go HClO2. We need to go HClO. We need to go HCOOH. That's formic acid. We need to go HF and HCl. Okay, conjugate acids. Now we're given the pKa's of each one. HClO2 is 1.95. This is pKa. This one is 7.54. This one is 3.74. HF is 3.17. And HCl is 3.1. Excuse me. HNO2 is 3.15. We're not given HCl. So what's HCl? Close to infinity. It's completely dissociated in water, strong acid, right? So if it's the strong acid, it's going to produce the weakest base. There's a trick there. We didn't include HCl in our list, but we did include it in the conjugate base. And you have to understand that HCl is a strong acid, so its conjugate base is going to be extremely weak. Now, if we were to compare the rest of these, right, if I got sneaky and asked you a question that didn't include this one, and I said, which one of these without the chloride would be the weakest base, it would come from the strongest acid. Okay? Strongest acid, weakest base. If we don't include the chloride, that would be the weakest because it comes from the strongest acid, produces the weakest conjugate base. All right. Let's see. Oh, yeah, I got one here. Here we go. Number 38. Carbonic acid is a diprotic acid, H2CO3. The first Ka is 10 to the minus 7th. The second one is 10 to the minus 11th. The ion product for water, we already know that, 10 to the minus 14. What's the OH minus concentration of a solution that is 0.18 molar in sodium carbonate? All right. So let's see, what are we given? We're given H2CO3. H2CO3 at, we're actually given sodium carbonate at 0.18 molar. Yeah, we're given sodium carbonate at 0.18 molar. But the Ka's for the acid, the Ka1 for this one is 4.2 times 10 to the minus 7. And the Ka2 equals 10 to the minus 11. 10 to the minus 11. Okay. We already know the Kw for water. And what's the hydroxide concentration of a solution that is 0.18 molar in sodium carbonate? All right. Let me refresh my memory on this one. Just a second. Okay. I just wanted to confirm what I thought originally. This is a case where we're going to go methodically through the species, the major species that are in solution before any reaction occurs. So we've got major species here, sodium, right? We've got carbonate, 2 minus, and we've got water. Okay? So we know that sodium's not going to react, right? It's a spectator. So we've got a competition here between carbonate and water. So what would the carbonate do? Well, the carbonate is coming from a weak acid here and a weaker acid here. So it's going to be a strong base. That means it's going to attack any water molecules and produce HCO3 minus plus OH minus. Now, the competition is for water. Like water plus water yields H3O plus OH minus. And this is the Ka. what's the KB? It would be 10 to the minus 14 divided by 4.8 times 10 to the minus 11. That would be the KB for this reaction, all right, because we're going backwards. This is going forwards, right? Ionization of an acid. This is going backwards. We're taking the conjugate base of the second ionization, which is what we start with our major species, and we're going backwards. So we need to know the KB for this reaction. So let's see, 1 exponent minus 14 and 4.8 minus 11. This is 2.08 times 10 to the minus 4. So this is the KB, 2.08 times 10 to the minus 4. And this reaction is competing with it as a Ka, which is 1 times 10 to the minus 14. So which one's going to win? This one right here. Right? So we don't have to consider this reaction as a competition. It's far too weak. It's still there, obviously, but it's so weak, it's not going to control the pH. So what we need now is our ice table. What are we starting with here? Well, this is 1-to-1 here to here. So 0.18 molar is our starting position here. And water's a liquid, so it doesn't count. And this one, which way is the reaction going to go? We head that way because this is essentially 0 compared to what we can do with it. Okay, so the change is going to produce one of these, plus x, and this is going to be minus x. Right? So 0.18 minus x, and this is x, and this is x. So now we can put our KB expression together. 2.08 times 10 to the minus 4 equals, right, hydroxides and bicarbonate over carbonate ion. And these values are going to be x and x over 0.18 minus x. Okay? This is going to leave us with a quadratic. Now, the question is this value small enough so that we're going to have x is going to be so small that we can ignore it for this term? Well, let's see what happens if we do. So if we say approximately x squared over 0.18 is equal to 2.08 times 10 to the minus 4, then we say 0.18 times that value, take the square root, and that will be x. That will be our hydroxide concentration. So I'm going to say 2.08 exponent minus 4, and then 0.18 times that, take the square root. And I get x equals 6.12 times 10 to the minus 3 molar. All right. All right. Best answer there is A. Now, we're assuming that we've met the 5% rule. But if we really want to be sure, we would substitute this x into here, and here, and here, and compare it to this value. So if we do that, if we put this x in here and in here, what do we get? Right? So let's say, I'm going to enter that, and then I'm going to say times. That's in the numerator. And then 0.18 minus that's in the denominator, divided. That would give us 2.15 times 10 to the minus 4, which is 0.07 away. 0.07 enter, 2.08 divide times 100 is 3%, 3.4%, 3.4% error. So we're within the 5%. Okay. Now the note there says compare the first KB and the second KB. Let's just do that to be complete. So what would be this is the KB2. What's the KB1? Well, that's 10 to the minus 14 and divided by 4.2 times 10 to the minus 7. And that would be 2.38 times 10 to the minus 8. 2.38 times 10 to the minus 8. Right? So there again, that secondary reaction is not going to have a significant impact on the pH or the hydroxide concentration, because this one is a much larger number than that one by 4 orders of magnitude. And it's a much larger number than the water, which would be 10 orders of magnitude. So this one is the one that controls the pH. All right. About 39. Get this out of the way, clear the board. Let's say 39. All right, calculate the pH at equivalence for the following titration. 0.1 molar hypochlorous acid with its Ka and 0.1 molar sodium hydroxide. Right. Let's see, get a drink. For titrations like this, you need to break it down into 2 steps. One is do the stoichiometry first, because that tells you what's left in solution that now establishes equilibrium. So we're going to do, let's say, what do we have first? We have 0.1 molar HOCl, 0.1 molar hypochlorous acid, and 0.1 molar sodium hydroxide. Okay, so we've got a monoprotic acid and a monohydroxyl base, and they're both the same concentration. So we should see a titration curve, something like we're going to add base, should be something like this. Right? We've only got that one curve. So what we want to know is what's the pH at equivalence? Equivalence is right here, right? Where the moles of base equal the moles of acid. All right. Oh, we're also given the Ka for the acid. 3.5 times 10 to the minus 8. 3.5 times 10 to the minus 8 equals the pKa. All right, so when we start off, say begin and end, we've got our titration is actually this, in aqueous solution in sodium hydroxide. And this is going to produce sodium hypochlorite, which is bleach. right? Sodium hypochlorite plus water. But bleach is a salt, but it's a solution of a salt. So we're starting off here with 0.1 molar. Well, in order to do the titration, we're not given the volume. Right? If we knew the volume that we started with, we could use that. But if we're not given the volume, then we just pick a volume. Right? Say we started off with 100 milliliters of acid. Right? 100 milliliters. That means 0.1, since they're the same concentration, you're going to need 100 milliliters of base. So 100 milliliters is 0.1 liters, and you're going to start off with 0.01 moles. 0.01 mole. For that, you're going to use that up, right? You're going to use those two up and end up with, you're going to use those up. At the end, you're going to have 0 here and 0 here. But what are you going to have over here? You started with 0. Now you're going to end up with 0.0100 moles of sodium hypochlorite. Okay? Well, if it's 0.01 moles in 100 milliliters, right? 0.0100 moles per 100 milliliters is 0.1 liter. Right? So that would be 0.100 molar of sodium hypochlorite. Okay, what does that mean? It means that sodium is a spectator and the hypochlorite is the active ingredient. Now we've got a base. We've got a new calculation here. This is the stoichiometry. This is the equilibrium. And for the equilibrium, we've got OCl minus plus water yields HOCl plus OH minus. Okay. All right. Now we can set up our ice table since this is an equilibrium. At this point, we're saying we don't have any hydroxide to speak of, and we don't have any hypochlorous acid. Right? We've used it all up. But now we've set up an equilibrium. So this is approximately a 0 to start with, and this one is 0.100 molar. Right? We're going to gain some of this. We're going to lose some of this. So we have 0.100 molar minus X, and this is going to be X, and this is going to be X. So what is the equilibrium constant for this reaction? Right? It's not Ka, it's Kb. The Ka for the acid is 3.5 times 10 to the minus 8. The Kb equals 1 times 10 to the minus 14 divided by 3.5 times 10 to the minus 8. That's the constant that we need. 3.5 exponent 8. And this is 2.86 times 10 to the minus 7. Okay? So now we can set up our equilibrium expression. I'm going to remove this so I can put the calculation over here. So the Kb, and I'm not going to draw out the whole thing. I'm just going to put the value for Kb. And then what do we put it in these positions? Well, it's X times X and it's divided by 0.1 minus x. Okay. Now, with the 10 to the minus 7, I think we're safe in approximating this as x squared over 0.100. So that means x squared is going to be 0.1 times that, which would be 2.86 times 10 to the minus 8. Right? We multiplied by a tenth, which made this not minus 7, minus 8. Now we just take the square root of that value. And let's see, it's already in my calculator. Oh, except I have to do this. There we go. Now the square root is 1.7 times 10 to the minus 4. That's the hydroxide ion concentration. What was the question? What's the pH? So what we need is POH first, which is the negative log of the hydroxide. Negative log is 3.77. And then the pH, subtract that from 14, is 10.2. There's your answer. Well, rounding error. 10.1 is the best choice out of that bunch. Okay? That took several steps. That titration is a good place to use stoichiometry first, then equilibrium. Oh, that's it for chapter 14. So let me go over here. Chapter 15. And we've got 12 of these highlighted and plenty of time. So let's change that. Clear the board. Okay, this is chapter 15. And let's see. Beginning with number 4. Let's see. A weak acid, HF, that's true, is in solution with dissolved sodium fluoride. Okay, we've got a solution made up of HF and sodium fluoride in solution. If hydrochloric acid is added, which ion will react with the extra hydrogen ions from HCl to keep the pH from changing? If we've got a mixture of these two, then we're looking at this equilibrium. Okay? We've got fluoride ions and HF. Since it's a weak acid, we'll have some of this and we'll have some of that. If we add hydrochloric acid, what are we adding? We're essentially adding a spectator chloride, which will react with the sodium. Well, it'll produce a sodium chloride solution, but it'll also produce hydrogen ions. Hydrogen ions are going to react here and drive the reaction backwards. So it's going to react with the fluoride ions because a weak acid makes a strong base and it will accept protons readily. Number 5. Which of the following is true for a buffered solution? Remember what a buffered solution in terms of pH, in terms of hydrogen ion concentration. A buffered solution is one in which the pH is close to constant, not constant, but close, changes very little with either the addition of excess acid or base, either one. So, which of the following is true for a buffered solution? A through E. What does A say? The solution resists change in its hydrogen ion concentration. Yes, it does. That's true. B says the solution will not change its pH very much, even if a concentrated acid is added. That's also true. C, the solution will not change its pH very much if a strong base is added. That also is true. And D, any hydrogen ions will react with the conjugate base of a weak acid already in solution. That's most often true. Right? With a few exceptions. When you produce a buffered solution from a weak base and its conjugate acid, actually a strong base and its conjugate acid, then you could get a buffered solution. But for most cases, D is also true. And that means that they're all true. Right. Let's see, we'll skip down a little bit, say number 8. How do the pHs of buffered solutions compare? Oh, we're comparing solution 1 and solution 2. So solution 1 versus solution 2. What's in solution 1? Solution 1 is 5 molar acetic acid and 5 molar sodium acetate. So this is 5 molar acetic acid. How do they write that? HOAC. That's a common abbreviation for acetic acid. This is the acetate ion, and this is the acid proton right here. And 5 molar sodium acetate. Solution 2 is 0.05 in both of them. 0.05 molar HOAC and 0.05 molar sodium. Okay, 8. How do the pHs of the buffered solutions compare? Well, A says the pH of buffered solution 1 is greater than that of the buffered solution 2. How do we know? What's the easiest way to determine the pH of a solution? The Henderson-Hasselbalch equation. It says that the pH equals the pKa for the weak acid plus the log of the base, in our case would be that anion, divided by this concentration. Okay? So, what does that mean? This is a constant for a temperature. This is the only variable. And the variable is the ratio of conjugate base to acid. So if these two values are equal, then this term drops to 0. And the ratio here, in our case, the ratio is 1. 5 to 5, 0.05 to 0.05. So this is 1, and that term dropped to 0. So both solutions have exactly the same pH. Which one leads to that? C. The pH of buffered solution 1 is equal to that of buffered solution 2. So that's C. Now, if I were to ask you a question like, which one has the larger buffer capacity? In other words, which one can withstand the addition of more acid or more base than the other? And you would go with solution 1. It has a much larger buffer capacity. Number 9. Which of the following is the net ionic equation for the reaction that occurs during the titration of nitric acid with potassium hydroxide? All right, nitric acid is titrated with potassium hydroxide, correct? Is that what it says? Yep. What will be the reaction? Stoichiometry here is double displacement. K goes with nitrate. Is that soluble? Yes, it is. And H and OH makes water. Remember when we were first semester chemistry, we were doing molecular equation, complete ionic equation, net ionic equation. The complete ionic equation would be this plus this, because it's completely soluble, this plus this produces this. And this. And water is non-dissociated there. Okay. This is the molecular equation. This is the complete ionic. The net ionic then would be, cross out the spectators. You've got potassium here, potassium there. You've got nitrate here and nitrate here. What is left over? What's left over is hydrogen ions plus hydroxyl ions yield water. That's the net ionic equation for every acid-base titration. So E is your answer. Okay. Let's see, number 10. Now we're starting to get a little weak. Try this. 10. In the titration of a weak acid HA with 0.1 molar sodium hydroxide, the stoichiometric point is known to occur at a pH value of approximately 10. Okay. So we've got equivalence point at about 10 pH for this reaction. Which of the following indicator acids would be the best to use to mark the end point of the titration? So if you want an end point at or approximately 10 pH, what do you need for the pKa? You need the pKa to be close to pKa approximately 10. Close to the same pH at which you reach the equivalence point. So which would be the best? Well, let's see. If we're going weak acid with a strong base, generally speaking, if you're looking for base added to weak acid, you go like this. The best place for your here would be the pKa if you were right at the equivalence point, which would be great. But since you're coming in from underneath, you want something here and maybe a little bit higher. So you generally go pKa a little higher if you have to. The other way around, if you've got a weak base and a strong acid coming the other direction, you would go a little lower for the pKa of your indicator. Okay, so if we've got a pH of 10, what does that mean for the Ka of the acid? The Ka would have to be approximately 10 to the minus 10. Right? I just took the anti-log of this negative. So that means that we would need, let's see. Oh, wait a minute. I'm looking at the wrong one. B, excuse me. The Ka would have to be close to, or maybe a little, well, the closest one, actually, this is an easy one. Because -6, -8, -14 are nowhere near 10 to the minus 10. The closest one is 10 to the minus 11. So that's the one you would go for. You would go for B. 10 to the minus 11 would be your best choice. If you had a 10 to the minus 10, that would be great. But if you didn't have a 10 to the minus 11, say you had a 10 to the minus 12, you would still go with the 12 because it's closer to 10 than 14 or 8. Well, actually, 8's on the low side. Actually, on the high side. Well, it's a moot point here. We've got the best one is 10 to the minus 11. I shouldn't be giving you any problems that require that type of nuance. All right, number 13. Okay, which of the following solutions would be described as a buffer solution? All right, remember what's required for a buffer. Generally speaking, you need a weak acid plus conjugate base. Right? The same rules apply for the acid conjugate base pair. But now we have to consider the concentration also. And the concentration should be close to 1 for the conjugate base ratio with the acid. So let's see which ones fit that. A, let's just put them up here. A, B, C, D, and E. What do we have for A? For number 13. Well, let's see. We have acetic acid, CH3COOH. That's another way of writing acetic acid. Right? We normally say acetic acid is HC2H3O2. Same formula. This representation gives you a little more information because if we draw it out in structure form, it would look like that here. Then this is connected to that carbon. That has a carbonyl and an alcohol group. That's a carboxylic acid. This is the acidic proton, right here or here. Okay, just so if you ever see it again, you won't be thrown. All right, now that's a weak acid. So if we add that weak acid and a strong acid, you're going to get a buffer? No way. Can't happen. How about B? You got 0.25 molar weak acid and 0.2 molar sodium hydroxide. That's a good one. It's not perfect, but it's acceptable. Why? Because if you have 0.2 molar sodium hydroxide and 0.2 molar acetic acid, you've neutralized 0.2 molar of the acetic acid, and you only have 0.05 molar left of the acid. So the ratio here is going to be very large. right? It's going to be at the extreme end of the buffer zone, but it will still work. So B is a good candidate. How about C? Sodium bromide and HBr. HBr is a strong acid. It doesn't matter what you put with it, you're not going to get a buffer. Ammonia plus sodium hydroxide, they're both bases. That won't work. And the last one, hydrochloric acid and sodium hydroxide are strong acid and strong base. That won't work. So out of those, your best answer is B. Here. 14. Okay. Let's do this. What do we got there? We still got some acetic acid, so I'll leave that up there. Number 14. All right, question is, which of the following would be classified as a buffer? Okay, again, the first A says strong acid and a salt. That will not make a buffer. Second one is acetic acid, 0.1 molar acetic acid, and 55 milliliters of base. What's that going to do? They're the same concentration. You add more base than you need, you're not going to be buffered anymore. You're past the equivalence point. It won't work. C, you got 0.1 molar acetic acid, 50 mils, and 25 milliliters of strong base. There you've neutralized half the base. I mean, half the acid. So you've taken this and turned it into that, only half of it. So now you do have a ratio of 1:1 because you titrated only half of the available acid. Now what you've got is what's left of the acid and an equal amount of conjugate base. C is your best answer. So we can assume that D and E are not right. Let's see. 0.1 molar acetic acid for D and 0.5 milliliters of very weak base. That won't get you anywhere near the buffer zone. And you can't add acid to acid for E. Right. All right. So this is based upon the species that you're adding together. This is based upon concentration. You're not getting into the your titration curve. You're still down in here with D. Okay. 19. Clear the board. Okay. Let's see. Consider these following indicators, and they're given their best color change range. Now, rule of thumb is plus or minus 1 pKa units or pH range. Plus or minus 1 pH is generally the physiological range at which we determine color change. But some of these are more pronounced, and you can pick up the color change in a narrow pH. So we're actually giving you the values here. So methyl orange is 3.2 to 4.4, methyl red is 4.8 to 6, bromethymol blue is 6 to 7.6. Phenolphthalein, you're familiar with that one, 8.2 to 10. Alizarin yellow is 10.1 to 12. So assume an indicator works best when the equivalence point of a titration comes in the middle of the indicator range, okay? For which of the following titrations would methyl red be the best indicator? Methyl red is 4.8, 6.0. (4.8 to 6.0 pH for methyl red. And we've got a selection of A through E for 19. All right. This type of problem is not something that I would give you on exam, because to work this out in detail, you would have to do the point of the pH at which equivalence occurs for each one of these A through E. And that will take half an hour at least. Right? So what we want to do is instead assume that it's already been worked out for you. And for 19A, well, A is easy. You've got the molarity of a strong acid and strong base. You know the pH there is going to be 7. pH 7.0 at equivalence. What we're looking for is a pH at equivalence that falls within that range. That's what we're after. Aniline and hydrochloric acid. Aniline is a base. We're going to titrate it with acid. And all of those are worked out in this document. If I ask you to do just one of these, that would be valid. But to solve this entire problem, that would be like a final exam test question. Right? You just get one question and you have to do the whole thing, and that's your grade. I've seen that before. Actually experienced that before. But in this case, the aniline is going to will reach equivalence for aniline and hydrochloric acid at 2.94 pH. Okay, that's not within the range. This is not within the range. How about C, where you have a weak base, ammonia, and a strong acid, hydrochloric acid? And that equivalence occurs at 4.63. That looks like a good candidate. It's not quite there, but it's close. Okay. This is possibility. How about the next one? HF and sodium hydroxide, right? HF is a weak acid. Sodium hydroxide is a strong base. So when we work that one out, just like we did a previous problem, we did stoichiometry and then equilibrium. We end up with 7.92. Right? So that's well outside the range. And then E is acetic acid and sodium hydroxide. And that's the one you're going to do, not this lab, but the next lab. And we worked that one out at 8.72. So if these are the only choices you have, the best one is this one. We start to get a color change about 4.8. So you're not too far past your equivalence point when you get to the color change. And out of that selection, let's see, methyl orange would have been 4.4. Methyl orange would have been iffy. Methyl red's kind of iffy. Sometimes what you can do is combine two. Combine the methyl orange and the methyl red. Then you're going to get pH changes that not just one color to one other color, but you might go through 2 or 3 colors. And that will tell you when you've actually reached the correct pH. Some indicators are pre-mixed that way. All right, so let's move on. Number 23. Okay. 50 milliliter solution of 0.035 molar hydrocyanic acid with its Ka is titrated with 0.033 molar solution of sodium hydroxide. What's the pH of the acid solution after 15 milliliters of titrant have been added. Okay. So we've got hydrocyanic acid titrated with sodium hydroxide. So hydrocyanic acid is titrated with sodium hydroxide. And this is the stoichiometry for the titration. Sodium cyanide is a product which is soluble, and water. Okay. So we're starting off with HCN at 0.035 molar, 0.0350 molar, and sodium hydroxide is 0.0333 molar. 3 molar. Okay. And we're told we want to know the pH, and we're given a clue there of the acid solution after 15 milliliters of titrant have been added. What's the titrant? The titrant is sodium hydroxide, 15 milliliters. We're starting off with 50 milliliters here. Okay. Let's see, we've got, let's not throw away any significant figures here. And 15 is also four significant figures. There we go. Okay. So initially, or to begin, what do we have? Well, 50 times 0.0350 will give you the number of millimoles of acid. And this is a 1-to-1 reaction. So 0.035 and 50 is 1.75 millimoles. And this is 15 times 0.0333 is 0.49. Actually, rounded off is that millimoles. Okay, that's what you begin with. Now, begin and end. What happens after the titration? Well, since it's 1-to-1, we're going to use up all of that base. It's going to be gone, consumed by this acid. So this is going to be down to 0. And this is going to be minus 0.500. Right? Because they're 1-to-1, when we use this up, we're going to use that up also. So this is 5 to 1.25 millimoles. Now, what reaction is going to occur? We've got cyanide in solution, and we have no base left over, but we still have some of this. So what do we have over here? Well, if we used up this much millimoles of that, it shows up over here. So we had to start with, but now we have 0.500 millimoles. Okay? That's the stoichiometry. The equivalence works from concentration. So what we need is to make concentration here. We have 50 plus 15 is 65 milliliters. And remember, millimoles divided by milliliters is molarity. So 1.25 divided by 65 is 1.92 times 10 to the minus 2 molar. And this is 0. And this is 0. Well, let's see. We just divide that by the same volume, 65 milliliters. So it's 0.5 divided by 65 is 7.6 1.69 times 10 to the minus 3 molar. Okay. That's the stoichiometry. Now we can set up an equilibrium. So I'm going to have to erase this to do that. Let's see. We've got, let's see, I'm going to erase this part up here. Now that we have cyanide ions in solution reacting with water, it's an equilibrium with hydrocyanic acid and hydroxyl ion. Okay, so what's the concentration, initial concentration of cyanide ions? It's this value, 7.69 times 10 to the minus 3 molar. Oops, not correct. There. And the hydrogen cyanide, or the hydrocyanic acid, is 1.92 times 10 to the minus 2 molar. And this is essentially 0. Okay, now we can work our equilibrium. Okay, what kind of change can we expect? Well, since we essentially have no hydroxides, reaction's going to the right. Okay, so we're going to lose some of this, and it's going to show up over here like that. And that gives us 7.69 times 10 to the minus 3 minus x. This is x. This is x. And what's the K for this reaction? It's not Ka, right? We're not going this direction. We're going this direction. It's Kb. Kb is 6.2 times 10 to the minus 10. Kb, 6.2 times 10 to the minus 10, divided into 10 to the minus 14. So that Kb is equal to 1 exponent 14 and 6.2 exponent 10 minus 10. There we go. 1.61 times 10 to the minus 5. Okay. So if we set up our equilibrium expression, we should see this. This is equal to x times x over 7.6. Oh, excuse me. My mistake. 1.92 times 10 to the minus 2 plus x. So let's go back and get it in here correctly. 1.92 times 10 to the minus 2 plus x times x over 6 times 10 to the minus 3 minus x. Okay. Now, if we work this the way it's going to give us a quadratic. And let me see. Let me save some time here and see what I did. 23. All right. I worked it out as a quadratic one way, and then I used Henderson-Hasselbalch for the other way. What we're saying is, now that we have this in solution and that in solution, we could also do this. pH equals pKa plus the log of 1.92 times 10 to the minus 2 divided by, oh, excuse me, that's not right. This is the conjugate base. This one, 7.69 times 10 to the minus 3 over 1.92 times 10 to the minus 2. There we go. Now, the pKa is this value right here. So 6.2 times 10 to the minus 10. Yeah, that's right. Okay, so we should be able to calculate the pH from this. 7.69, and let's see, let me scroll just a little bit and get these in the right position. Then flip them and divide. So this is going to give us, this right here is 4 times 10 to the minus 1. We'll take the log of that and then add it to this. 6.2 exponent minus 10. And I get, that doesn't look right. Oh, I know what I did wrong. This is the Ka. We need the negative log of that value. There we go. Now I got 8.81 pH. And that would be C. So we could have worked it out like this and done this equation. Right? Worked it out the long way using the ice equilibrium procedure. But the Henderson-Hasselbalch, once we know what the concentration of the conjugate base and the acid are, this is much quicker. 25. A certain indicator, HIN, has a pKa of 9, and a color change becomes visible when 7% of it is IN minus. And what pH is this color change visible? All right. Let me see. The way I worked it out here. All right. So remember that most indicators are weak acids, and they undergo their equilibrium reactions right alongside the titration. So they have their pKa's also, and they have their equilibrium expressions that are valid also. So what we've got here is H indicator is an equilibrium with IN minus plus H plus, and the pKa equals 9. Okay. It's saying that the color change begins when 7% of the molecule is IN minus. So if we start with a certain amount here, we start from, say, 100 here, start. And then the color change becomes visible when this is 7 and this is 93. The way I worked it out here makes the wrong assumption. What it's saying is, let's see, IN minus over HIN is 0.07 or 7%. Right? That's not strictly true. The way it's written, the question is written, it would be this is equal to 7 divided by, 93. Hopefully, we should get the same answer or very close to the same answer. So I'm going to work it out this way, and we'll see, compare it to the values that we got of the answer that's expected. If we work it out this way, then the Henderson-Hasselbalch says this, and here's the conjugate base, here's the acid, and if we want to know the pH, then the pKa for this would be 9. Okay? That's given. And then we have the log of 7 over 93. So let's do that calculation and see if it comes out to the one that we would have expected, 0.07 rather than 7 divided by 93. Let's see. 7 and 93 divide, which is 7.52 or 53 times 10 to the minus 2. And then take the log of that and then add 9. And that gives us 7.88. Now, what's the one that's expected here? 7.85. Okay, so if you did it that way, the best answer is D. But if none of these is there, right, and you select none of these and I count it wrong, then you have an argument for counting it right. You just have to make that argument. It's poorly worded. Yeah. It's like whoever wrote the question was thinking one thing and they didn't write it clearly. All right, that was 25. Next is 26 and 27. 26 and 27 in the figure below. Okay, 26 and 27 are both based on the figure below. 26 and 27. 26 says in the figure below, the pH at first hydrogen equivalence. So we want the pH at first equivalence. Okay. And 27 says the acid would best be used in a buffer near pH. Buffer near pH. Then we have selections, A through E. A, B, C, D, E. And our choices are 1, 4, 6, 10, and 12. Okay. All right, so let's go down and look at our drawing. This is a titration curve for a diprotic acid. You know that because there are 2 equivalence points. There's one equivalence point at C, right? And there's another equivalence point at E. All right, but what we want here is what's the pH at first equivalence point? That should be close to 6. Right, so if we go back up here, 6 would be C. That's C, or 6.02 is the answer given. That's the first equivalence. Buffers, where would it buffer best? The buffer would either be here at B or here at D. And yeah. So it'd be B or D. So B is at about 2. 2.6, maybe. 2.6 is a possible. Or D, which is about 9.7. Right? So I think D is probably the best answer for that one. Right? D. 10, pH 10 would be the best buffer region. Because you're still, once you get up to 10 right in here, you're still in the buffer zone. Okay. That's 27. And oh, that's it. Any questions, comments? Let's see. So on Thursday, since we have a lab on the same day as the exam, take the exam in person. So we'll have the exam in person, and then we'll go. I don't have anything else scheduled, I believe. Let's see. Right. We'll take the exam in person, and then we'll go in and do Le Chatelier Principal Lab. So be sure you understand what you need to do. Right? You don't have to put it in your notebook because this is informal. But definitely read the procedure and understand the steps that you're going to have to go through. And if you want to put it in your notebook, that's perfectly fine. Writing it down like that may reinforce the procedure. Then you won't have to be cookbooking it the whole way through and just stumbling all over yourself and your neighbors. And then we'll come back the following Tuesday and pick up with chapter 16. And I'll hand out the, maybe this Thursday, I'll hand out the next lab, so you'll have plenty of time to prepare for it. Yeah, that's what I'll do. Okay, so we're a few minutes early. If there are no questions, then we're done for today.